Now, we've spoken already about the dependent variable y and the independent variable x, and we've spoken about the parameters, but we haven't really said anything very much about this stochastic disturbance term. But since obviously y not only depends on x, but it also depends on u, we need to be specific about how the ut are generated. What are the properties of ut? Or rather, what do we assume about those properties? So once again, just to reiterate, ut appears in what we call the population regression function. So ut appears only in the population regression function, and one implication of that is that we never actually know what the true disturbances, the true UTs are. So we have our population regression function, yt equals alpha plus beta xt plus ut. These UTs are the unobservable disturbance terms. Now, these UTs are the population disturbances. But once again, we never actually observe those because we can't observe anything about the population regression function because we don't have the population of data. What we in fact use when we want to get an idea about these disturbances is the sample counterpart to the disturbances, which we call the residuals. So the residuals are something which we can obtain from our model. The population disturbances are something which we cannot. But in order to show that the ordinary least squares estimator has a number of desirable properties that we'd like an estimator to have, we need to make a certain set of assumptions about the unobservable disturbance terms. Obviously, we make the assumptions about these unobservable disturbance terms. We don't make the assumption about the residuals. Obviously, we don't need to assume anything about the residuals because we can get hold of these residuals from our estimated model. So there are a number of assumptions we make about these unobservable error terms. The first and simplest of these assumptions is that we assume that the disturbances have zero mean. So their expected value or their average value is zero. Secondly, we assume that the disturbances have constant and finite variance. And in particular, we assume that the disturbances don't have a variance which is a systematic function of the explanatory variables. Clearly, if that were the case, that would be an example of the U's not having constant variance. Thirdly, we assume that the covariance between the disturbances is zero. So in other words, there are no patterns or relationships within the disturbances. There's no relationship between the ith and jth disturbance. Another way to say that is that we assume that the disturbances or the errors are statistically independent of one another. Finally, we assume that there is a zero covariance between the disturbances and the explanatory variables. So there's no relationship between the error and its corresponding x variable. This makes lots of sense because I said earlier that the x's, the explanatory variables, are non-stochastic or fixed in repeated samples. And clearly, if something is non-stochastic, it cannot be correlated with a random variable u. If the covariance between u and x were non-zero, this would mean that x was related to a random or stochastic variable, and therefore it couldn't be non-stochastic or fixed in repeated samples. Now, in order to show that the ordinary least squares estimator has this set of desirable properties that I'm going to speak about in a moment, we just need these assumptions 1 through 4. In order to make inferences from the sample regression function to the population, that is to address questions of the form, is it plausible that the true but unknown value of beta could be 1 or 2 or whatever, we need to make an additional assumption. And in particular, we need to assume that the disturbances follow a particular statistical distribution. Now, we need to assume that they follow a particular statistical distribution so that we can apply some statistical distribution theory later on to test these hypotheses that we might be interested in about the true but unknown population regression function. Typically, we assume that the disturbances are normally distributed. There are other possibilities, but these other possibilities are inherently much more complex. So for this course, in order to be able to make inferences from the sample to the population, we assume that the unobservable disturbances follow a normal distribution. Note that this fifth normality assumption is not required to examine the properties of the OLS estimator, only if we want to test hypotheses about the unknown population coefficients. Now, why do we need these assumptions about the unobservable error term? Well, the answer is we need these assumptions in order to show that the OLS estimator has a set of desirable properties. If these assumptions 1 through 4 hold, then we could show, although we're not actually going to do the algebra required, we could show that the estimators alpha hat and beta hat determined by ordinary least squares are what's called best linear unbiased estimators. So the acronym that refers to this desirable property of the OLS estimator is BLUE. So if these assumptions 1 through 4 hold, then the OLS estimator is BLUE. So what does this acronym actually stand for? Well, taking the letters B, L, U and E in a slightly different order, first of all, we could show that beta hat is an estimator of the true value of beta. So in other words, beta hat, we have a formula under ordinary least squares for beta hat, which will give us a guess or an estimate of the true value of beta. So beta hat is an estimator of the true value of beta. Secondly, beta hat is a linear estimator. This means that beta hat is a linear function of the random variables. Now, if we look at the formula for beta hat, you may think, well, the formula for beta hat is a nonlinear one. So it's a nonlinear function of the random variables. But that's not true. In fact, if we look more closely at the formula for beta hat, the only random variable in that formula is y. X, remember, is a non-stochastic or non-random variable. So beta hat is a linear estimator because it's a linear function of the random variables y. And similarly with alpha hat obviously is an estimator of the true value of alpha, and alpha hat is a linear function of the random variable y. Thirdly, the estimators for beta hat and alpha hat under ordinary least squares are unbiased estimators. And what that means is that on average, the actual value of alpha hat and beta hat will be equal to their true values. Now notice we're not saying that the estimated values for alpha hat and beta hat will be equal to the true values in every sample. Clearly that won't be the case. What we are saying is, on the other hand, if we take many, many samples from within the population and we calculated the average value of alpha hat and beta hat from within those samples, then the average values would be equal to the true values if we took enough samples. Another way to say that is that there's no systematic bias in the values of alpha hat and beta hat that we estimate. In other words, we won't always predict alpha hat to be too big, and we won't always predict beta hat to be too small, for example. Sometimes our alpha hat will be too big, sometimes it will be too small, and on average, if we took many samples, these errors would cancel each other out. So this is the property of unbiasedness. Finally, the ordinary least squares estimator, under these assumptions about the unobservable disturbance terms 1 to 4, the ordinary least squares estimator is what we call best. Now in this case, best as a word has a very specific meaning. And best means that the ordinary least squares estimator for alpha hat and beta hat has minimum variance among the class of linear unbiased estimators. So what that means is, if we took many linear unbiased estimators, including the ordinary least squares one, the ordinary least squares one would be minimum variance. And one upshot of that is that, again, if we took lots of samples from within the population, the ordinary least squares estimator would lead to the smallest variation in our estimates of alpha hat and beta hat from one sample to the next, from among all possible linear unbiased estimators. Now, we could think of an estimator that had a smaller variance than the OLS estimator. For example, if we use the estimator that beta hat always equals 2, whatever the data say, this is an estimator because this is a formula that we could use to get the value of beta hat for each sample. So I'm saying, suppose we used an estimator where the estimator said that the value for the slope was always going to be 2, whatever the data said. Clearly this estimator will be a minimum variance estimator. It won't have a variance at all, it'll have a variance of 0. Because whatever the data say, whatever the samples say, we're always going to take the same estimate. But this would be not an unbiased estimator. In other words, it would be a biased one. Because suppose that the true value of beta were actually 3. If we use this estimator here, then this would be systematically biased, because for every single sample, our estimate would be too small compared to the true value. So this would be a minimum variance estimator, but it would be biased. The ordinary least squares estimator, on the other hand, gives us minimum variance among all linear unbiased estimators. So we could find perhaps a nonlinear estimator with a smaller variance. We could find a biased estimator with a smaller variance. But we can't find a linear unbiased estimator with a smaller variance than the ordinary least squares estimator. So this is clearly a desirable property that we'd like our estimator to have, because we don't want the coefficient estimates to vary too much from one sample to the next. And of course we want our coefficient estimates to be unbiased. Another way to state this blue property is to say that the ordinary least squares estimator under assumptions 1 through 4 is consistent, unbiased and efficient. Now, consistency is a slightly weaker condition than unbiasedness, but it's slightly similar. We could show, using some fairly technical algebra, but we don't need to do this on the course, we could show that the ordinary least squares estimators for alpha hat and beta hat are consistent. What that means is that asymptotically, in other words, as the sample size is increased towards infinity, the estimates will converge upon the true values. So in other words, as we increase the sample size from the minimal number of observations required to estimate the parameters, which in the bivariate case will be just 3, towards infinity, then our estimates would gradually converge upon the true values. So that if we had an infinite amount of data, which of course we never will, then we would get to the true population values. There's a technical piece of notation which we can use to state the consistency property, and that involves a probability limit. And that says the limit, as t tends to infinity, of the probability that the difference between the estimated value beta hat and the true value beta being bigger than delta, which is some arbitrary distance, equals 0. So in other words, the probability that beta hat and beta are more than an arbitrary distance delta away from each other tends to 0 as the sample size tends to infinity. A stronger condition than consistency is unbiasedness. Now, I've spoken already about unbiasedness. Unbiasedness is a stronger condition than consistency because unbiasedness applies to small samples as well as large samples. Consistency only applies as the sample size tends to infinity. Unbiasedness, on the other hand, applies for any size of sample. So we can say unbiasedness is a stronger condition than consistency. And technically, we could say that unbiasedness applies if the expected value of the estimate, alpha hat, equals its true value alpha, and if the expected value of the estimate beta hat equals its true value beta. Then if those two things hold, then the ordinary least squares estimator is unbiased. And these two things will hold if the assumptions 1 through 4 hold. Finally, an estimator is said to be efficient if it is unbiased, and no other linear unbiased estimator has a smaller variance. Once again, we could say that efficiency implies that the variation in our sample estimates from one sample from within the given population to another will be minimized for the given that we have a linear unbiased estimator. We could also say that if our estimator is efficient, that means we're minimizing the probability that our estimate will be a long way off from the true value. So once again, you can see that consistency, unbiasedness and efficiency are desirable properties that we want our estimator to have. We want our estimator to always have these properties, and it will only be guaranteed to have these properties if the assumptions 1 through 4 that we make about the unobservable disturbance terms actually hold. Any set of regression parameters that we estimate will be dependent upon the sample that we used. That means if I have a particular set of data from within the population and I use that to estimate the regression model, and you have a different set of data and estimate the same model, but that sample of data is from the same population, then the chances are you and I will get different estimates. Now, in an ideal world, we'd have many, many samples from in the population, and we'd compare between them, and we could see how much our alpha hat and beta hat estimates change from one sample to the next. However, in practice, we're only ever likely to have one sample of data from within the given population. So what we'd like is an idea of how robust or reliable our estimates are and how much they are likely to change from one sample to the next. And there is a quantity known as the standard error which gives us this information. So the standard error, and there will be a standard error associated with each of the parameter estimates that we've got, tells us how likely it is that the sample parameter estimates will vary from one sample to another, but using only information contained in the one sample that we've got. So we have a set of formulae or expressions for calculating the standard errors for the intercept and the slope parameters, and we could derive those algebraically using the same kind of approach as we did when we derived the coefficient estimates themselves, but I don't actually bother to do that on this course. So if you want to go through the algebraic proofs, and for those of you who have strong backgrounds in maths, I'd recommend that you do that, then go and have a look in one of the textbooks. In my textbook, this is done in the appendix to chapter 3. However, what we're going to do for the purpose of this course is simply to consider what elements are in the formulae for calculating the standard errors and why do these elements appear in the formulae in the ways that they do. So if we look at the formulae for the standard error estimators for alpha hat and beta hat, we'll realise that those are once again a function of the data. That is, they're a function of the actual observations on the explanatory variable xt. They're a function of the total number of observations, capital T, and they're also a function of something that we haven't yet met, which is usually denoted by the letter S. Now, S is an estimate of the standard deviation of the disturbances. And we need to talk a little bit now about where this S actually comes from. Now, hopefully we remember from last time our equation for the population regression function. Now, the population regression function described the true relationship between the variables. Now, once again, we have to note that we never actually observe this true population regression function. Now, just as we'll never actually know what the true alpha and beta that represent the true relationship between the variables is, similarly, we can never get an idea of what these true population disturbances are. So we could call these things the population disturbances, but we cannot actually get an idea of what these are. So instead, what we do is to replace them in any equation where we need to get an idea of these by their sample counterpart. And the sample counterpart to these is known as the residuals. So the residuals we met during the last lecture, and these were the bit of the data that the model couldn't explain. So those were defined as the difference between the actual observation yt and the model fitted value for yt. So once we've estimated alpha hat and beta hat using the sample regression function and the ordinary least squares formulae, we can then calculate these residuals. And obviously we'll have one residual for every observation that we've got. So, just to recap, obviously, once again, we'd like to know what these true population disturbances are, but we never actually know those because we never have the whole population of data. Instead, we have to use the sample counterpart, the residuals. So coming back to what we were talking about, S, or S squared, what are we trying to do here? Well, what we're trying to do is to get an estimate of the variance of the disturbances. Now, if you remember, the equation for the variance of any random variable u is the expected value of, open brackets, ut minus expected value of ut all squared, close brackets. Now, under the first assumption of the classical linear regression model, which is that the expected value of the disturbances is 0, then the second term inside the square brackets will cancel away. So we'll have the variance of the disturbances equals the expected value of the squared. Now, because an expectation is simply an average or a mean value of a series, we could think of taking the expected value of the squares of these disturbances by simply taking the average of those squared disturbances. So one way to estimate S squared would be to take the average value of the squares of the disturbances. But once again, to come back to the point I was trying to make here, we never actually observe the population disturbances, and therefore that's not a workable definition. What we do instead is to replace the disturbances in the formula for calculating S squared by their sample counterpart, which is the residuals. So our estimate for the variance of the disturbances is simply the average of the squared residuals. Now, unfortunately, it turns out that this is a biased estimator of the variance of the disturbances. In other words, asymptotically, or as the sample size tends to infinity, will be okay. But for small samples, this could give us the wrong answer, systematically. Therefore, we use a slightly different formula. And instead of taking the average of the squared residuals, we take the sum of the squared residuals, and instead of dividing that sum by t, we divide that sum by t minus 2. And the reason that we divide by t minus 2 rather than by t is that this is sometimes known as a degrees of freedom correction. And we'll go into this in a bit more detail later on, but for now we have to note that when we estimate our regression model, in order to be able to calculate the residuals, we needed to estimate alpha hat and beta hat. And obviously we've estimated two parameters here, one for the intercept and one for the slope, and therefore we need to divide by t minus 2 rather than by t in order to take into account the fact that we lose 2 degrees of freedom when we estimate these two parameters in this equation here. So I'll explain a bit more about what degrees of freedom are later on, but for now all we need to know is that when we calculate S squared, we divide by t minus 2 rather than by t. Okay, so an unbiased estimator of sigma, that is an unbiased estimator of the standard deviation of the disturbances, is given by the square root of the residual sum of squares, which is obviously sigma u hat t squared, divided by t minus 2. So what I want to do now we know what S is to go through the standard error formulae element by element, and just to try and develop some intuition as to what lies behind the formulae and what lies behind the elements of those formulae being in the formulae in the way that they are. So first of all, we note that both the standard error of alpha hat and the standard error of beta hat depend on S. Why do they depend on S? Well, this is probably best illustrated using two diagrams. And we're going to use two similar diagrams in many instances here to again explain why the formulae contain the elements that they do. So remember that S or S squared were both functions of the residual sums of squares. So what I want to do is to plot two fitted lines to some data here, one for a situation where the residual sum of squares is relatively large, and one for the situation where the residual sum of squares is relatively small. So in both cases, let's suppose that this is our fitted line, and let's try and keep the values of x constant in both of the diagrams. Obviously, I should add here that in both cases we plot x on the x-axis and y on the y-axis. So let's try and keep the values of x constant across the two, and just suppose that the values of y were different, so that in this case they're more dispersed than they are in this case. So if I try and draw that, here we want the residual sum of squares to be relatively large, and that would mean that the points all taken together lie a relatively long distance away from the line. So let's just draw 5 points, and similarly on this diagram here, let's draw 1, 2, 3, 4, 5 points. So what we can see is that the residual sum of squares in this first case is relatively large. That is, the sums of the squares of the distances from the points to the line are relatively large. Now, if I were to ask you the question, which of these two sets of data do you think is likely to lead to a more accurate or reliable or robust set of coefficient estimates, you'd probably and hopefully reply to me the second set. And that would be the correct answer. The reason is that if I were to now try and draw another line, not the line of best fit, but just any other line, and apply it to this set of data, in the first case I could do that fairly easily. So for example, I could draw another line on the data, and you would have a hard job in saying to me that this green line was a very bad fit to the data compared with the black one. On the other hand, if I did the same thing in the second case here and I drew the same green line onto the diagram, you can see now that the green line lies a much further distance away from all of the data together than the black one does. So in the first case here, when the residual sum of squares is relatively large, we can say that we've got poor determination of the coefficient estimates. In other words, we can't be very sure that the fitted line is an accurate one. In the second case here, on the other hand, we've got all of the points lying very close to the line, and therefore it would be very hard for us to draw another line that's a long way away from that and still say that that line fitted the data relatively well. So what does that tell us about the standard error formulae? Well, the answer is we need to think and to look at the formulae, and we see that both of the standard error formulae, that is the one for the intercept parameter and the one for the slope parameter, both depend positively on S. That is, they'll both depend positively on the square root of the residual sums of squares. Therefore, if the residual sums of squares rise, then the standard errors rise. Now, the standard errors give us an estimate of the unreliability or lack of precision of the coefficient estimates. So what we want to see in a regression model actually is standard error estimates that are relatively small for given coefficient estimates. So for our coefficient estimation to be accurate, we want the standard errors to be small, and that would partly arise from a small residual sum of squares, as we have in this second diagram here compared with the first. The second element that appears in both of the standard error formulae is the variability of the explanatory variables about their mean values. So once again, the easiest way to get an idea of why this is relevant to the value that the standard error takes, we need to compare across two diagrams. So in the PowerPoint slides, I plot two different diagrams, one where the explanatory variables are very narrowly dispersed about their mean value, that's the diagram on the left, and another one where the explanatory variables are very widely dispersed about their mean value. In the first case, on the previous slide, we were interested in the vertical distances from the points to the line, which would be embodied in the residual sums of squares. Now, in a sense, we're interested in the distances horizontally from the points to their mean value. So if we were to again ask ourselves the question, which of these two diagrams is likely to lead to more accurate and more precise coefficient estimation, once again we'd probably argue that it would be the second case. And the reason is, again, if I were to try to plot some other line onto these diagrams, it would be much easier for me to do that in the first case than in the second case. In the second case, the line is very close to the data points, and the data points are very well dispersed. So if I were to change the intercept and slope parameters, we get a line that clearly wouldn't fit the data. In other words, we can say that the coefficients have been very well determined. On the other hand, if we look at the diagram on the left, all of the points are very bunched together. So I could kind of pivot the fitted line around about the centre of x bar and y bar, so that I would change the slope and the intercept as well, but pivoting on that mean value x bar, y bar, we could get a line that with a very different intercept and slope to the original one, but one which doesn't look as if it fits the data very badly. So that being the case, once again, the second diagram where the points are very well dispersed will lead to smaller standard errors. And if we look at the standard error formulae, both the formula for alpha hat and for beta hat both contain the sum of squares of x about the mean value, that is sigma xt minus x bar squared, in the denominator, that is on the bottom of the formulae. So the bigger sigma xt minus x bar squared is, everything else being equal, the smaller the standard errors will be. So that's the second element in the standard error formulae. The third element in the formulae is the number of observations t, capital T. Now, usually in econometrics, we assume that every observation that we have represents a useful piece of information. And that being the case, the more observations we've got, the more information we've got in order to be able to reliably and accurately estimate the coefficients. So we'd expect, given that intuition, that the larger the number of observations, everything else being equal, the smaller the standard errors should be. Now, certainly for the standard error estimator for alpha hat, we can see that that is indeed the case. In other words, capital T appears explicitly in the denominator for the standard error of alpha hat. So the bigger the number of observations we've got, the smaller the standard error will be, and the more reliable or robust and precise the coefficient estimation for the intercept will be. Now, although the capital letter T doesn't appear explicitly in the standard error estimator for beta hat, it appears implicitly. And the reason is that in the denominator for the formula for estimating the standard error of beta hat, we've got the sum of xt minus x bar squared. Now we need to think again about what we're summing over. Well, we're summing over all of the observations from lowercase t equals 1 up to capital T. So the bigger the number of observations capital T, the more elements there will be in this sum. And because we're always squaring the elements here, the more elements we've got, the bigger this sum will be. Therefore, the bigger the denominator will be, and the smaller the standard error will be. So once again, even though it doesn't appear explicitly in the formula for the standard error of beta hat, the larger the number of observations we've got, the smaller the standard error will be. Finally, we've got a term sigma xt squared appearing only in the formula for the estimator for alpha hat. And the reason that this formula appears in the standard error formula for estimating the standard error of alpha hat is that it measures the overall distance of the points to the y-axis. Now, once again, if we were to draw two diagrams to try and illustrate what's going on, and therefore which of sigma xt squared being large and sigma xt squared being small will matter, we could do that as follows. So let's consider two lines which we're trying to estimate. One where sigma xt squared is large, and one where sigma xt squared is relatively small. So once again, let's try and keep the line and everything else the same. And in this case, we want sigma xt squared to be small. Well, sigma xt squared measures the variability of x about 0, if you like. Or it measures how closely all of the points taken together are to the y-axis. So if we first of all think about what sigma xt squared small would look like, that would mean that all of the observations lie very close to the y-axis. On the other hand, let's take a set of points and put them over here where they're equally spaced from one another compared with this diagram, but where they're now further away from the x-axis. So if I do the same thing, let's say we've got 1, 2, 3, 4, 5. So the dispersion of the points about their mean value is the same here. The only thing that's changed is their distance from the y-axis. Now, if I were to ask you which of these two is likely to lead to a more accurate slope estimate, the correct answer to that question would be that the slopes in both cases would be estimated equally accurately or equally inaccurately. And the reason is that the bunching of the points between themselves is the same in both cases. The only thing that's changed is their distance to the y-axis. So therefore, the only thing that will change is the standard error estimator for alpha hat. Now, the standard error estimator for alpha hat will be bigger in the second case because it's much harder in the second case here to determine with accuracy where this point is. So this is the intercept here. This is the point where the line crosses the y-axis. And once again, I'd have a very hard job to move this line around here and still us to be able to say that it accurately represents the data as a whole. On the other hand, I could probably move the line a bit here. Even if I move it very slightly, this line is still within all of the points, but you can see that the intercept has changed quite a bit. Therefore, only the standard error formula for alpha hat is influenced by sigma xt squared, and if sigma xt squared is larger, then the standard error will be larger on the intercept parameter, and therefore our estimation for that intercept will be less accurate. What I want to do now is to have a quick look at a very simple example. And that simple example shows us how to calculate the values of alpha hat and beta hat for a given set of data, and also how to calculate their standard errors. Now, in some ways, the example is redundant, because in any practical situation, we'd always have a computer which would estimate these things for us. But let's suppose that we've got a set of data on some variable y whose movements we were trying to explain by reference to some other variable that we'd also got data on called x. And let's suppose that we got 22 observations or data points in our sample. And let's also suppose that in a spreadsheet we've calculated the sum of the observations on x multiplied by the observations on y. We know that the total number of observations t in our sample is 22. We know that the mean of the observations on x, or rather we assume again we've calculated in a spreadsheet, is 416.5. And let's assume that we've calculated that the mean of the observations on y is 86.65. Let's also assume that we've calculated sigma xt squared by taking each individual observation on x, squaring it, and then adding them all up across the 22 observations, and that is 3,919,654. Finally, let's also assume that we know the residual sum of squares to be 130.6. Now, there's a slight inconsistency in my example there, because obviously, if we wanted to calculate the residual sum of squares, then from the formula I put up on the board earlier, we realised that we'd already have to know what the intercept and slope parameters were. But let's not worry about that for now. Let's just suppose that we've calculated the residual sum of squares and it's 130.6. The first thing what we want to do, given this data, is to calculate the values of the intercept and slope parameters. Now, we simply do that by plugging the numbers into the relevant formulae that were in the PowerPoint slides previously. And if we do that, we get an estimated slope parameter of 0.35 and an estimated intercept parameter of minus 59.12. Remembering that we write the fitted line as y hat t equals alpha hat plus beta hat xt, then we can write the fitted line, obviously, replacing alpha hat and beta hat with the values that we've estimated using these formulae. The next thing that we have to do, given that we know what the residual sum of squares is, or rather that we can calculate it, is to calculate the estimate of the standard deviation of the disturbances. So once again, we use the estimate from the residuals rather than from the true disturbances, because we don't know what the true disturbances are. So this quantity, the standard deviation of the disturbances, is also sometimes known as the standard error of the regression. And that's the terminology that's often used in papers and in computer packages. So we calculate this by taking the residual sum of squares, 130.6, dividing by 20, and then taking the square root of that. And so S for this example is 2.55. Once we know what S is, once again we can very simply calculate our estimates for the standard errors for alpha hat and beta hat, and these turn out to be 3.35 and 0.0079 respectively. So the way that we write these results, always in econometrics, is to write our equation for the fitted line and then to write in parentheses below the coefficients the standard errors to which they correspond. So 3.35 in parentheses denotes that that's the standard error estimate for the slope, for the intercept, and 0.35 has below it 0.0079, and that's the standard error estimate for the slope parameter. So once we've calculated those two things, that's how we actually write them down. And once again, that is the notation and terminology that's used in the econometrics literature predominantly.